Okay, so can you guys all see my screen here?
Yes.
Great. So I want to start with talking about a really major example of an algorithm, and I want to use that to demonstrate some features of the algorithms that I think are shared by quite a lot. Algorithms is where this really starts to multiply into really endless algorithms. So let's just talk about what we mean by an algorithm and some of its features. So for optimization, I think you can think of a lot of algorithms as iterative. That means we're going to do something over and over and over again. So gradient descent is a good example of an iterative algorithm. What gradient descent does to find an optimal solution is, well, you're going to have to start with an initial guess point. In fact, in basically every optimization algorithm, you have to seed this algorithm with initial guess of where you're going. Gradient descent then works with a really easy idea. So here you have this picture on the left, and the gradient, the sign actually kind of works out flipped here. So if the gradient's pointing up, we want to go down the hill. We want to go down the hill, and by going downhill, we're going to arrive to something that might be good. You can kind of immediately see a weakness of this. So this picture on the right shows you. So it's a good idea, you know, if you keep traveling down the hill, you are definitely going to end up, if it exists, at a local minimum. But you might get stuck in some ruts along the way. So you can imagine this going to the right local minimum here. So you could get stuck in a not very globally optimal local minimum, but you are going to get a local minimum. And as I said, most algorithms like this can only promise you that. So with gradient descent, you start with an initial guess, and then we're going to iterate it. So we're going to do this some number of times, and we're going to pick our direction. So this could be sometimes more generally thought of as your search direction. So I'm going to search this function in that direction and try to get to a better point. So we have our search direction, v, and that's given by the gradient of our function. You could minimize your step size or not, but let's just start thinking of it as a step size at first. You're going to go in the direction v, some step size s. If you minimize that step size, then you have an adaptive step size, and that's kind of another, subtlety, improvement to add on the algorithm. But the general idea is just we're going to start at, point x, xi, and we're going to define the next point, xi plus 1, as going downhill that direction, v, and that step size, s. So it's a pretty simple algorithm, but it actually underpins a lot of other algorithms. So you can make this a little bit more and more powerful. So I already kind of mentioned it with this adaptive step size. There's also stochastic gradient descent. So this gradient, it's all good when we do our next example of a single variable function. And we'll look at another two variable function. With one or two variables, it's not a challenge to compute this gradient over and over again. But with a high dimensional function, like a neural network, you're not going to want to compute this 1,000 element gradient for every single iteration of your algorithm. So you might sample from the gradient. And so that gets you something like stochastic gradient descent. When you have stochastic gradient descent and you have adaptive step size, you could also add in second order terms. So the gradient, you can think of that as a first order term. There are other terms, various sometimes called momentum terms, that can speed up the convergence of this algorithm, at least theoretically. If you add in all of those, you start to also get some other algorithms that you might have encountered by different names. So for example, if you ever run a procedure optimizing a training neural network, you might use ATOM. And the ATOM algorithm is essentially stochastic gradient descent with adaptive step size plus some momentum terms. So gradient descent is a pretty good example of the idea of a lot of the algorithms. So I want to show you guys how to implement that on Matlab. But that would be the only one I'll show you how to implement on Matlab, because I also want to show you a very powerful tool that will get you guys easy access to a bunch of the available algorithms for all those different problem types I talked about, or at least all the finite dimensional problem types. So this is going to incorporate a bit of a Matlab tutorial. And I don't really know the strength of the Matlab for you guys. So I'm going to throw a little bit of the code at you, but to make it a little more accessible, and also to show you guys another powerful tool, I'm going to use Matlab's live script option. So step one, and if you guys have Matlab, it's probably the most useful thing is for you guys to open it up and kind of implement this as you go along. And then at the end, if you had any issues implementing or mimicking what I'm doing, then you can ask me about it. So step one, let's open a new live script. I don't know if you guys have seen Matlab's live script thing, but it's actually really powerful. And it's pretty neat. It's kind of Matlab's entry into the whole notebook scene. So Mathematica has long had a really powerful notebook. And then the Python community has lately kind of been, paid homage to the Mathematica notebook and created Jupyter Lab and Jupyter Notebook. And now Matlab has a notebook. And all of these notebooks kind of work in a really similar way. So you can type some input. So, x equals 10 into some cell. And Mathematica calls them sections, not cells. And you can run that section. There's also key shortcuts. And then it'll do the output. You can do the output on the right here or underneath. Let me make my font a little bit bigger, actually. And then you could do a new cell, and the cell keeps what you had before. So if I wanted it to output, 2 times x, then it would output using that before. They all also share the fact that you have to rerun the cells if you want values to change. So if I change this to 20, but I don't rerun that cell, then this, should still oh, well, okay, it didn't quite do that. Well, to some extent, I think I just ran them both instead of one because I did the wrong keyboard command. But you have to go back and actually run the cells again when you change them to get the next cell to change. So this isn't very exciting with 2x and x equals 20, but it's a great way to start displaying your content. So for example, I'm going to plot a function really quick that we're going to run gradient descent on. So I kind of pre-typed this function to save us some labor, but we have x squared times cosine of x minus x, and the whole thing is going to be divided by 10. So I'm going to plot this function. And it's a little better on the right. So this is the function that we're going to work on applying gradient descent to. I think you can already see some traps lying in wait for gradient descents. So we have a one-dimensional function, and we're going to therefore just need its derivative for gradient descent. So I've gone ahead and typed that too, although feel free to point out if you see any mistakes in this gradient. Okay, so step one, to apply gradient descent, we need to define the gradient. It's worth mentioning that this step can be very non-trivial for many optimization problems. Can you actually compute the gradient? For a neural network, you have to use automatic differentiation and compute the gradient, as the some component total of that neural network. So it can be very challenging to compute the gradient. And I've already mentioned that sometimes you do a stochastic estimation of the gradient. But we have one-dimensional calculus, so the gradient is not that hard. So now to do gradient descent, I'm not going to do adaptive. I just want to do it for some step size. So I'm going to go ahead and set my step size to something that seems like a starter. So let's say my step size is s equals 0.2. And then I'm going to set up a for loop. So I want to do actually keep showing you these. So you can split these cells. So you can keep some of these computations separate from each other and just run your for loop cell over and over again without pre-computing all of this. Okay, so we're going to set a step size. And we need to set an initial guess. So I'm going to make an initial guess. Now, we're going to fiddle with all of these to show both the success of the algorithm and the breakdown of the algorithm as you use it for the wrong settings. So you can really see how, even if you have an algorithm available, you might not have a very robust algorithm available, and your parameter tuning and initial guess makes a lot of difference. But first, let's be reasonable and try to make a good initial guess. So I can see that this right side solution is the one that I probably want. And so let's see, that looks to be about 10, but let's make it a little farther away. So let's say we're going to choose 7. We'll make x naught equals 7. And now let's get a for loop here. So Matlab has very easy for loops. Let's just do 10 iterations for now. And for each of those iterations, we're going to have our step size be given by our derivative function. So just evaluate this. So I've started at x naught. I'm just going to keep using the x naught variable and redefining it. So we take the derivative at that value. The semicolon in Matlab just suppresses the output so that this doesn't print that value over and over again. Then I'm going to, actually, let me add in some plot commands. I want it to plot all of this. And at each point, I want it to plot x naught and f of x naught. Okay, so if you're plotting a point in Matlab, it's worth mentioning you always have to add a marker style, or else your point will be an infinitely small invisible point. So make sure to add something if you're plotting a point in Matlab. Okay, so that's just to also makes debugging really easy if anything goes wrong with this. So now we have a very simple update rule. So we're going to keep updating our value, which I'm going to call x naught just over and over again. And so it's going to equal what we had minus s times v. And I'm going to plot that new point as well. And looks pretty good. And I'll add an output here at the end so that we can see what our final guess was. All right, so you can see it starts up here. Here's our first one, here's our second one, third one, and the 4th through 10th have already converged so much that we can't even see the difference. And our final answer here, I haven't solved this analytically, so I can't give you an error bound, but looks like basically we exactly solved this problem. So that's obviously pretty good. Now let's break this. S equals 0.2 worked really well. So let's do one that seems less likely to work. Let's make a bigger step size. Now, you don't always want a smaller step size. There's a lot of sense in making a bigger step size if you want to search a larger space. But in this case, I believe that should break us. So indeed, it doesn't plot very well, but what happens is it goes down over here, but then it overshoots and then goes way over here, back over here. So the step size of 1.2 is much too large to ever fall within this valley. So that's kind of the first way that you can break it. And you can see the downfall of too small a step size as well. You're not off the wrong path, but you are taking a really long time to get there compared to the first step size we talked about. So this is a feature that a trade-off feature and a design feature that you're going to find as a challenge in many, many optimization algorithms. And it's, of course, why there's also a large literature devoted to how we optimize these step sizes and to adaptive step sizes. So you imagine if you have a multivariable case, some of your variables might have very different ranges. And very different fluctuations. So for some variables, you might need a very small step size, whereas for others, you might have a range of a couple thousand and you want a very large step size. So step size always needs to be adaptive and relative to your data. Okay, so we've seen that. Now let's break this in another way. So let me set this back to 0.2. That seems pretty good. Now let's change our initial guess. So let's go over to -5. You can see it really didn't take much effort to get it stuck in this suboptimal valley. And that's not surprising given the algorithm. It's going to get stuck in any of these ruts that you start near. Now, there are ways to overcome that too. So this is a good way to look at what approaches you might use for global optimization. Global optimization approaches are often much more ad hoc, but that doesn't make them any less effective. So I think on the fly, we could design a pretty good global optimization algorithm for this. So what I would do, and what a lot of them do, is, well, we've seen a solution for 2 different initial guesses. I could easily construct a program that did 1,000 different initial guesses and then compared them all. And if you think about it, each of those initial guesses and running the initial guess for that algorithm is completely separate from all the other ones. And by that, I mean, we can parallelize it. So with parallel computation, we could take this simple gradient descent program and turn it into actually a pretty effective global optimization program. Certainly for this function, it would take much less than 1,000 initial guesses to find the global optimum. And with parallel computation, it's really not a problem to scale this so much for larger dimensional functions. So that's one way we can turn this simple local optimization algorithm into a global optimization algorithm. So I want to show one more example with gradient descent, and then I'll show you the tool that will then make you perhaps think that you'll never have to implement your own optimization algorithm again. You would be wrong. But let me open up, save this one. And open up a new live script. And now let's do a 2-dimensional function, because it's helpful just to see how this works for that, and to do one that actually uses the gradient. I think that you'll very rarely ever have the opportunity to do it with just a single variable. Oops, it's my pre-computed answer there. So let's get this up and running with a multivariable case. So I'm going to save us some time and cut and paste over a function and its derivative. And I made my font very large for my shared screen to work, but if you ever encounter in Matlab a place where it goes off and you really wish you could take 2 lines to do this, you can use ... in Matlab, and that lets you do a line break without ruining the code. So, all right, so we defined f and we defined df. Now let's make a pretty plot of this so we can see what kind of function we're in for. And I'm going to do a surface plot of this function. And I saw a couple names that were in a couple of my classes, so they might be feeling humor because I generally don't allow any of the students to use any of these nice f-plot functions or anything, and I force them to parameterize everything. But for this shortcut course, it's good to know the easier shortcut tools. Okay, so this makes a very pretty nice plot of our function here. And we can see, at least in this domain, there's a pretty clear region that should be our local minimum and that we want gradient descent to converge to. And there don't even look like many pitfalls for gradient descent. So first, let's make a initial guess. So we're always going to have this initial guess. And I'm going to pick an initial guess of, not a very good initial guess, because I want to make my algorithm work a little bit. So I'm going to pick the initial guess 2, 2. So it looks like that should be up the hill here from our valley. And let's pick an initial step size. I think actually this is doing a weird section thing. Shows. I think I got it switched into text somehow. We'll worry about that when we click run. So let's do a step size here of 0.25. And now let's write our gradient descent. So I just want to point out, in case you haven't done the gradients, so I did pre-write it for you guys. But if you squint here, this semicolon means that this is a column vector. So actually a better place to end the line might be to emphasize this column. So here's the top element, and those are all the partial derivatives with respect to x. And here's the second one, and these are all the partial derivatives of the function with respect to y. So df is going to return a vector of the gradient with respect to x and the gradient with respect to y. And so we have, let's make sure this is, got something kind of weird here. Just gonna copy and paste, save here. We have some weird. Okay, I haven't actually used this notebook all that much, so we somehow got into text mode, and there's some simple toggle that will save that, but I'm just gonna switch files. Okay, so we have an initial guess, we have a step size, and now we're just gonna implement gradient descent. So if I implement gradient descent for this, I'm gonna get, let's do it for I equals, let's see the chat here. Do you need to, so in the chat, the question is, do we need to derive the gradient function manually in Matlab when conducting the gradient descent optimization? And the answer is often no. So I don't have a prepared demonstration of it, but one thing that Matlab now has is a symbolic toolbox. And you can, using that symbolic toolbox, if you, I don't think you can avoid much entering in your function. So you do have to be able to symbolically enter in your function there, possibly in a slightly different format for symbolic toolbox. But then you can use its symbolic differentiation to construct the gradient. So you actually don't have to do the gradient by hand anymore. And also another way you can do it, and sometimes you'll have to do it, is numerically. So you can even tell the algorithm to numerically estimate the gradient from your inputted function. So not in this for loop version that we're writing, but in the actual available Matlab optimization routines, there's usually the option for the routine itself to numerically estimate the gradient. So there are a bunch of ways to avoid actually having to manually compute the gradient. Good question. But for this class, for this example, I just wanted to do the for loop. So I'm going to keep the gradient there. So we're going to do the same as we did before, say like 15 iterations. And we have our direction, which is going to be the gradient evaluated at our point. So as I wrote it, we're going to call it from our first vector value and our second vector value. A little kludgy. I could have written this as a vector value function, but I thought this would be a little easier to read. So we're going to get our gradient direction. Then this outputs a vector, just like our initial guess vector. And I just switched it so that they're matching. So this should be a column vector. And just like this function was defined as a column vector. And now we are going to update this. So x0 equals x0 minus s times b. So still the same update rule, just written compactly, knowing that these are both now vectors. All right, and I actually am going to take a little bit of a shortcut here because I wrote a little bit of a nice plotting routine, and I'm going to copy and paste it over because part of it is just to add in a nice line. So this is same update. So this intermediate one is just so that I can draw a nice line between our points so we can see where we're going. Let's see. And after class, I'll share these lab notebooks with you guys. So let's see what we get when we run it. Looks like I didn't suppress some of my outputs. Let me suppress those outputs so that we can just get to our nice plot here. What else didn't I suppress? X naught. Here we go. So here's the result of our gradient descent. So each of these dots are where our next guess is at. And this red line is that extraneous code I added just to draw the line. So when you're in the live editor, you can manipulate all the Matlab figures just like you would be able to manipulate them as figures. So if you hover up here, you get this rotation button and you can rotate this. And if you ever find a better angle, they actually have all these options to incorporate it into your code. So I could update that view command to better see it. So you can see that this works pretty well. You can see that it's doing exactly what we would expect gradient descent to use. So gradient descent, I think, is pretty easy as long as you understand how to write it in terms of vector notation. It's very easy to implement it for n-dimensional functions. But that said, it is 2021, and you might want to use one of the more available solvers. So what you're really going to use, because this example, of course, is not including any constraints, and we can, as we've seen, get much more complicated. So Matlab, if you type this into, one way to get to the documentation is to type doc optim into this or the command line, or you can just search for the optimization toolbox. Matlab, unlike many a program, actually has wonderful documentation. Almost all of their functions have great documentation with lots of examples. And so of great usefulness is the optimization toolbox. This is where you're going to find a lot of the solvers for linear programming, nonlinear programming, all of the programmings that I mentioned. And so this is going to be really invaluable for any of your optimization problems. So if you start looking through this, depending on what kind of problems you had, so if you have a nonlinear optimization problem, if you have linear mixed integer programming, quadratic programming, they also have some functions specific to data fitting, like least squares. So you'll get just about everything you want. And it's in the forms of these different solvers. And one challenge can be finding the right solver. So if somebody doesn't tell you what solver to use, do you really want to go through all this documentation? So they have actually introduced this really great tool, and we can get it up and running in our live editor. So if you go to, I can't make the top font bigger, so I'm not sure how well you can see it, but on the top bar, there's something that says task, and you click the little arrow below it, and there's an optimization task. So we're going to click optimization. It takes a second to load. So we're going to let it load. And this is the amazing tool that got me grumbling about kids these days. This is pretty great. So what this is going to do is really open us up to all of the different solvers. And so you can see here, the options are most of what we've talked about. They do have their special least squares option, but they have different kinds of objective functions. Going with the function that I inputted up there, I'm going to choose nonlinear. And I want to repeat what we did here using their solver instead. So each time you click this, has the chance of changing what solver they suggest. So when I clicked nonlinear, they suggested fmincon, which is one that I've used in most of my research. It's the fmin, it's a minimizer solver, and it solves with constraints. So this is their main nonlinear minimization solver. Now, if I switched around here, if I chose linear, it would suggest their linear programming one, quadratic, presumably, yes, it would suggest their quadratic one. So just going to nonlinear here, I could also switch. So it includes in the constraints the variable type, which, as I mentioned, it's kind of interchangeable whether you want to define that as a variable space or as a constraint on the variables. So I could switch to integer programming here, and it would suggest this optimizer I've actually never used. And you can click here if you have nonlinear constraints. So it's, I don't know how I got into that. So I think I might have clicked global at some point. But anyway, we're gonna keep this. There we go. There, back to fmincon, just trying to get it. So it should stay in fmincon if you have nonlinear constraints, because fmincon includes nonlinear constraints. On the other hand, if you went back to your linear solver, it would start in this linear programming one, but then you tell it, I have nonlinear constraints, and then it goes to fmincon. So this really does a lot of the homework for you. It finds you the right solver. Now I'm going to unclick the constraints because the problem I just inputted didn't have constraints. And let me show you how to use this. What it does is also set up and tell you what you need to write for the solvers. So most Matlab solvers, you have to write the functions, of course, that you want it to solve with. Every problem needs to have its objective function quantified, defined. So we're going to define the objective function just to show you how to use this. So you could write it in a separate file, which will happen a lot if you have a big model that makes your objective function. You're going to kind of want to separate it into a separate script. I'm just going to use the one that we defined above. Let's see, I think that would be the function handle that we did above. So that would be f. And for our initial point, this is why I have this redundant variable here, because this always changed value, but I wanted this in my workspace. So that's our initial guess, and we're going to do that. So it makes it all very visual. You need somewhere to find f. I define it in a function handle. If I did a local function, here's what it does. I'm going to say a local function and click new because I haven't done it yet. And then it gives you the exact form that the solver needs. So here's your optimal optimization inputs, your variable inputs. It nicely extracts them for you, at least gives you an example of how to do it for this two-dimensional function. And then you would write your function. Now I'm going to go ahead and delete that because we've got our function up there, but that's how you would do it. So we've got our function f, our initial point, and let's choose some plots. I'm going to choose for it to plot the current point. That's the x value it gets in its iterations, and the objective value. Okay, and then you go up here and you can press it with this button or right click and press run over here. Let's see what we get. Hopefully not an error. The horror. Okay, so I know what that was. So we are going to write, I did have to do this. So we are going to write a little local function, translate. So it keeps bringing that up because I have this. Let me do this. So let me write the local function version. So you do have to get the, look at this. Not the nicest solution, but we have to make the format match. So let me just that's just still using our same f handle, but we have to make the format match this. Okay, run section. Select the objective function that we just wrote. Now it will run section. Define the function handle inside the function. It did seem a little easier not live, but these are pretty minor compared to using fminCon from scratch. So now let's see if we can get this to run. Aha! Okay, the window popped up over here, so let me see if I can get the fun part for you guys. So it actually shows you, it's running a little slow, but it shows you as the iterations go. These are our values. So our y value ends up being 0, and our x value ends up being, somewhere here, -6 point something. And this shows you the decrease in our objective function as it runs different numbers of iterations. So it's not doing gradient descent, it's doing whatever's under the hood of its NLP solver. You can get a remarkable amount of information out of this though. So for example, I can see that we're kind of flatlining here. I probably don't need much more than 15 iterations. This is good to know for defining your various values. So you can also specify a bunch of solver options. You can get really into the weeds here. You can specify, maximum iterations, maximum or minimum accuracy demands, and also look at, so this should be a fun plot, step size. It'll show you the adaptive step size changes. So a lot of information here that you can get. And you can also use this to find all of your solvers. It's really a great tool. So if I was going to add in just one more thing to add in as part of this demonstration, we want to add in a constraint. So let's make a lower bound constraint. So let me look at my function here. What lower bound might get us a little bit of fun. Let's force everything to be greater than 0. So that should, I think, rule out our original answer. And so you can do all bounds the same. and let's make x greater than or equal to 0. So we're gonna run it again with that. When this green light is on, it'll auto run every time you make a change. Which can be so you can actually see that it comes up with a totally different answer as you would want. Now, if you want to do a function constraint, what it's going to do is do the same demand that it did for an objective function. So for the objective function, it wanted you to write the function that is the constraint. For a nonlinear constraint, you're going to have to write a function, but it's going to give you the format. So let's click new. It gives you the format that you need. So I know the few students here from the class where I forced them to do this might be very appreciative of seeing this spelled out. So for fmin_con, it requires you to specify the equality and inequality constraints in the same function. So here it gives you this example. And so for our function, we might go in and write a different constraint. If you ever don't want one, you make it empty. So you would say, I have no equality constraints. So you set that equal to an empty array. So it's a really powerful UI. Now, for conversational purposes, so I'm going to end, I'm going to do a new live script. Managed to lose my main window here. Okay. So I wanted to give you guys a task just in the background if anybody wants to try to work with it. And I'm going to end the recorded part of the lecture so that you guys can ask questions. So let me open up the live editor in this one and give you an example function to optimize. So again, it takes a second to load here. Okay, so this function is actually the example it comes with. And it's a famous optimization problem. So we want to minimize Rosenbrock's function. And if you Google this, you can immediately get some pictures of this function. But I wanted to load this for you guys. And if anybody's interested and wants to stick around, I think it would be a good challenge for you guys to just try to optimize this function. So it's not very challenging at all to run this. So you should be able to get this up and running and click run, but see if perhaps you can at least plot the solution, or if you could maybe implement gradient descent, which I will put on the screen so that we'll actually put on the screen so that you guys can copy the gradient descent algorithm. And yeah. So on that note, I'd like to end the recording and open it up for questions. Yufeng, can you end the recording?